In our last brainstorming English, we improved the high linearity of the IMPI duty cycle with dual-edge interpolation. However, only both good linearity and good duty cycle was still not good enough for high-speed studies. Even though the last reference work did a good job, we can probably do better through deep thinking in their fundamental images. The goal here is to design a high-speed IMPI itself, and we may also show other state of art for your reference. Since we are focusing on the operation speed of the IMPI itself, could you look at both the single edge and the dual edge interpolation deeply? Then tell me which one is fast and why. You probably should narrow two different operation regions down to one clock period for 5 seconds or slightly longer. Bingo! Your eye visually tells you the dual edge interpolation requires 6 operation regions in 1 clock period. So it's much slower than the single edge interpolation in 3 operation regions in 1 clock period. So which operation region of the dual interpolation we can remove to speed up? Of course, we cannot remove the interpolation regions of either the variable slope or the constant slope of the range up and down. Therefore, we should be able to remove the retention state without integrating the charge to full or empty. What's more, great, removing the retention states seems also a big improvement in the circuit implementation. Remember that we connected both interpolation cells and the retention cells at V-int node, but enabled each cell exclusively. Thus, both S and R signals kept changing during different regions or different modes, integration mode and retention mode respectively, such that the interpreted waveform at V-int works properly from region 1 to region 6 in 1 clock period. Not only does squeezing so many regions in 1 clock period slow the clock frequency, but also the complicated control signal switching through feedback will limit the operation speed further. Without the retention states, those controls in an analog state machine could be gone, and we should be able to reduce the clock period. Think about how the waveform images without retention looks like for 5 seconds. Here we go. We call a simple microelectronics 101. If there's a square wave bidirectional current that charge and discharge a capacitor periodically, then a triangular shape is produced at the output voltage V-int. In an LTI system, a phase shift square wave input current should produce a phase shift triangular output based on the superposition of the inputs. These phase shift V-int voltage are interpreted based on the weighting. Also, if the interpreting V-int voltage have identical slope as the interpreted output keeps the constant slope as. On the other hand, if the interpreting V-int voltage have opposite slope sign S and minus S, the interpreted slope varies. To be straightforward, if the interpolation weights are linear, the slope variation should also be linear and a function of factor k. This interpolation therefore give rise to a family of piecewise linear PWL signals, which are linear space in time in the constant slope region. This concept operation shows dual edge IMPI without retention is doable. Alright, besides the simplified dual edge IMPI, we still need to pay attention to its input clock phase. In the single edge IMPI, we just need a quadruple phase input clock, but this reference approach applies a smaller phase spacing of 22.5 degrees between two input clocks, so the period divided by 16 for the variable slope region will relax the linearity requirement from the IMPI greatly. Unfortunately, to provide a 16-phase input clock signal, the power would be too high to operate at high speed and low jitter at the same time. Not to mention, distributing the 16-phase input clock to several IMPI is very challenging. Therefore, keeping a quadruple phase input clock is preferable in high-speed studies. Alright, after understanding another wish list of the quadruple phase input clocks for high-speed studies, let's exercise those images in the timing diagram and see if that's doable. To be clear, every IMPI should have the variable and constant slope regions. In region 1, both clock phases are large high, and both MOS are on to generate a constant output slope. In region 2, both clock phases are large high and low, and the top left PMOS and the bottom right MOS are on to generate a variable slope output. Again, I'll let you exercise if the constant slope is in region 3 and the variable slope is in region 4. As we expected in our wish list, two constant slope and two variable slope are generated in one clock period without using any control signals for different regions. Also, there are no retention or reset regions needed for this IMPI. Interestingly, in the variable slope regions, slopes are a function of K. For example, a current M minus 2K times I unit flows into the capacitors in region 2. It can be observed that as K varies linearly, the selected phase code also changes linearly by the 2K over M factor. Again, this linear increment in slope leads to linear voltage increment at the end of region 2, forming linear phase uniform voltage. Constant slope starting from the voltage base in region 3 will be linear space in time and also provides high phase linearity. After understanding the concept of the simplified and high-speed dual edge IMPI, we need to look for a doable circuit image. From the last experience, we got the slicer approach was simple and fast, but a high output impedance is required for a good current source of integration. The first topology increases high output impedance by transistor stacking, and the second one uses both resistor and transistor stacking. Again, from the Microelectronics 101, you may know only the transistor stacking provides better linearity in DNL owing to a higher output impedance, but the second one achieves a less jitter and has lower I-level change from the PVT variation with good linearity. Based on all the PVT conditions and the process node for your target speed, you may need to simulate in SPICE along with the iterative sizing to decide which topology may work better for you. Please leave your comments down below if you have such exercise experience. Here are the summarized images showing you why the simplified dual-edge IMPI can achieve high linearity and high speed operation at the same time more easily than the previous work. First, the retention or reset region of operation is removed. So, secondly, there's no control or feedback logic for the region's determination. Third, the input phase of the clock is also reduced to 4 instead of 8 or 16. Fourth, keeping the circuit image with a slicer-based topology simplifies loss of analog capacity, such as the voltage bias requirements for current source and analog calibration. Also, the slicer will scale with the advanced technology as the digital block. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share comments down below. Lastly, please share the video link with the people who may be benefiting from it.